اوكي. اسمحوا لي اولا ان اقدم عنوان الكتاب or the syllabus of the content of this course. Okay. This is the important topics that we want present to this course, to the course of operator theory. Okay, we will talk about Banach algebras, representation theorem for Banach algebras, spectrum theory, normal and compact operators, bounded operators on Banach spaces, and von Neumann algebras. Okay, and we can introduce many books in these topics, that we list these 6 books. One of these sources is a course in operator theory written by Conway, and also a course in functional analysis written by Conway, and the book by this title, Introduction to Banach Algebras, Operator and Harmonic Analysis, written by Dales and other writers. And also we found a new book that is very nice for you and it is very useful, Operator Theory by Example. Okay, it's written in 2023. And this book by the title An Element of Operator Theory. Okay, elements in operator theory, and the book for routine functional analysis. These books and many other books are useful for you, and we use some of these books for you. And also we have another books such as in the following. And this is the book that we begin with this source, and in the following we switch to the other source. Okay, let me write this for you. سأبدأ بهذا الكتاب فيما يلي. سوف نستخدم كتبا أخرى أيضا. Okay, do you understand, dear students? And also I sent this book for you. Please note that. سأرسل لك ملف الكتاب، ملف الكتب. Okay, let me begin with the part 1 of this book. Part 1, Banach algebras. Definitions. A Banach algebra is first of all an algebra. We start with an algebra A and put a topology on A to make the algebraic operation continuous. In fact, the topology is given by a norm. Okay, this is the definition of norm. Let E be a linear space or a vector space. A norm on E is a map such as this from E to real numbers, such that we have these three conditions. The norm of X is non-negative for any X in E, and the norm of X equal to 0 if and only if X equal to 0. The norm of alpha X equal to the absolute value of alpha multiplied by the norm of X for any scalar or complex. The norm of X plus Y is less than or equal the norm of X plus the norm of Y for any X and Y in E. If we have these three conditions, this is a norm. on E. Please note that this E is a vector space, okay, so that E is a vector space. Okay. E is a linear space or vector space, so that we have two operations such as so we have two operations such as plus from E times E to E that maps, for example, X and Y to X plus Y, and also a scalar multiplication from C times E to E that maps, for example, alpha and X to alpha X, okay, so that this alpha X is an element of E, okay, this is an element of E because E is a linear space and we have the scalar multiplication, and also we have this as an element of E because we have this plus operation. And we know many examples are in linear spaces and norm spaces. For example, C is on C because we have ordinary by the ordinary plus and scalar multiplication plus and or addition and multiplication on C. Ordinary addition and multiplication in complex numbers. And also in this vector space we have this norm for any z equal to x plus iy in C. We can write this equal to x2 plus y2. We know that this is a norm function, and this function from C to R have these three property. Okay, the absolute value of any complex number is non-negative and it is equal to 0 if and only if z equal to 0 and other condition. This condition is hold, this condition is hold, and triangle inequality hold in complex number. Okay, okay, it's very trivial that for any z in C, this is non-negative, this is equal to 0 if and only if z equal to 0. It is very trivial because if this absolute value equal to 0, this must be equal to 0, so that x and y must be equal to 0, so that z must be equal to 0 and vice versa. And this equal to in complex number for any alpha and z in C, and finally z1 plus z2 is less than or equal to absolute value of z1 plus absolute value of z2, so that it is a norm function or complex number, so that C with this is a norm space. Okay, is a norm space. If this is a norm on E, this order pair E and this norm function is called a norm space, and it is a Banach space if every Cauchy sequence converges in X, or if this norm is complete. Dear students, do you have my voice? Okay, and you know that if E and this node this is a sequence and this is a sequence in E is xn is called Cauchy sequence whenever we have this condition for any epsilon that exists a natural number such as n, such that if m and n be greater than n, then the norm of this subtraction xn minus xn is less than epsilon. And if we consider an element in A, we say that xn converts to x in this norm space whenever for any epsilon non-negative that exists a natural number such as n, such that if n be greater or equal n, then this norm be less than epsilon. Okay, it is very clear that if xn is a convergence sequence, then it is Cauchy. Okay, it is Cauchy. It is very trivial because if, and we denoted this by this notation the limit of xn equal to x or xn tend to x. Okay, now if the limit of xn equal to x, let me write by notation for each epsilon that exists n such that if n is greater or equal n, then we have this. Okay, epsilon divided by 2, because this holds for all epsilon. We can consider epsilon divided by 2. This is a non-negative real number 2. Okay, and this shows that for any epsilon there exists n, this n, okay, such that if m and n be greater or equal n, then this norm is less than epsilon. And this holds because we know that by triangle inequality this is less than or equal xn minus x plus, let me write more complete, this is equal to xn minus x plus x minus xn, and this is less than or equal xn minus x plus x minus xn, and both of these is less than epsilon divided by 2. Okay, and this less than epsilon. So any convergence sequence is a Cauchy sequence in any norm space. Now if any Cauchy sequence is a convergence sequence, we say that this is a complete norm space. Okay, it is a Banach space or complete space if every Cauchy sequence converges. Okay, then we say that this norm is complete and this norm space is a Banach space. Okay, and we have this definition. Let A be an algebra norm on A is a map such as this from A to A, such that this is a norm space, and further we have this condition: the norm of AB is less than or equal the norm of A multiplied by the norm of B. Okay, in this definition A is an algebra, so that in addition to these two operations, plus an scalar multiplication, we must have another operation. Okay, we must have another operation we must have three operation. Okay, x and y tend to x plus y, alpha x tend to alpha x, alpha is a scalar, let me write summing for you. This is from a times a to a, this is from c times a to a, and this is from a times a to a again. That maps x and y to xy. We need this operation too. So if we consider an algebra, we have these three operations. Okay, these three operations. And you know the definition of algebra. I only recall this for you, okay? Okay. We have these three operations in algebra. So we can write this in the norm of AB, because this AB is an element of A again. Okay? Less than or equal the norm of A multiplied by the norm of B. Please note that in this condition alpha is an scalar, or is a complex number, not an element of or linear space. Because in general in a linear space we don't have this operation, for example, okay, this operation. But in algebra, xy is an element of A for any x in A and y in A. So if we have this condition, we say that this is an algebra norm. This is an algebra norm. And the norm algebra A, and this norm is a Banach algebra if this is a complete norm. If this norm be complete, or every Cauchy sequence is a converted sequence, we say that this is a norm algebra. Okay, norm algebra. Okay, we can take many examples for you. But you can see some properties for algebra in this addition, such as these properties. This multiplication in algebra must be associated and have this distribution property a multiplied by b plus c equal to ab plus ac, and this equality, and for any alpha in complex number, alpha multiplied by ab equal to alpha a multiplied by b. Please note that a and b are elements in a. Okay, so that this multiplication must have these property. And you know the definition of algebra. This multiplication, this is addition, and this is a scalar multiplication. This multiplication with respect to this operation and this operation must have these properties, okay? Associativity and this distribution properties, this and these equalities, okay? Okay. And we mentioned that in chapters 1 to 7, we shall usually suppose that a Banach algebra is taught. By this definition, this means that A has an identity such as EA. This is the identity element of algebra A. Okay? So that, for example, for any A in A, EA equal to EA, A, and this is equal to A. This is the identity element for our algebra A. And also the norm of this must be equal to 1. The norm of this element must be equal to 1. Let A be a Banach algebra with identity. Then by moving to an equivalent node, we may suppose that A is unital. It is easy to check that for each norm algebra A, the map AB map to A multiplied by B is continuous. It is not that if we have the identity element with this property, we say that this A is unital, okay? And also please note that this multiplication is continuous, the multiplication operator in any algebra or node algebra is continuous, because if for example if we consider, for example, let me denote this function by h, okay? H from a times a to a by this function rule, h of x and y equal to xy, okay? Now if a sequence such as this tend to xy, we must prove that if then we have the norm of h of xn and yn minus h of xy equal to xn yn minus xy, and this is equal to xny minus xny plus xny minus xy, and this is equal to xn yn minus y plus xn minus x y, and this is less than or equal by triangle inequality xn yn minus y plus xn minus x y this norm multiplied by this norm, and this is this useful property, okay, for any a and bn in A, because we know that this xn and this are element in our algebra A, and also this is less than or equal this multiplied by the norm of y, and both of these tend to 0 because this tend to 0 and this is a bounded sequence, and also this tend to 0 so that this multiplication tend to 0. This shows that the limit of h of xn and yn equal to h of x and y. So for any sequence in this space that tend to x and y, we have the limit of h of xn and yn tend to h of x and y. Okay. This shows that this function is continuous, and also we know that other operation is continuous too. It is very trivial. For example, if we consider the operation of addition by car, for example, from a times a to a by this function roles, this equal to x plus y. It is very trivial that if xn and yn tend to x and y, then the norm of k of xn and yn minus k and xy equal to xn plus yn minus x plus y, and this is equal to xn minus x plus yn minus y. Now you can use only triangle inequality. This is less than or equal this plus this norm. Okay, and both of this equal to 0, so that this must be tend to 0. And also this operation, this is very easy and similar to the proof of this. It is write the proof of continuity of a scalar multiplication for each set. Okay, so that by this, dear students, do you have my voice? Don't have. So that these inequalities are very important and lead to the continuity of operation in any algebra. Okay, normed algebra, the multiplication operation is continuous too. So we can see many examples. Such as this example. Let S be any non-empty set, then CS, or the set of all functions from S to C. Okay, as an example, we can consider CS, or the set of all functions from S to C. This is the vector space, and also this is the algebra. We can define this operation for any F and G in this space, and for any alpha in or scalar numbers we can define F plus G, alpha F and Fg in this space by these definitions. For any x in S, F plus G of x equal to F of x plus G of x, because we know that if we consider F and G in this space, then F and G are functions from S to C, so that F of x and F of and G of x are complex numbers, and we can compute the addition of F of x and G of x. And alpha F of x equal to alpha F of x, and Fg of x equal to F of x G of x, because these two are complex numbers and these two are complex numbers, and we have multiplication operation in complex numbers. Okay, so we have this operation, and also we have the constant function 1, constant function from S to C by this function rule. This equal to 1 for any x, 1 of x equal to 1 in complex number. Okay, this 1 is the identity element of this space. Okay, because it is very trivial that F1 equal to quantitative unital algebra. Okay, dear students, I think this is enough for this session, and we can continue in the next session. Okay, do you have any question, dear students? It is not that we can consider a subset of this space denoted by L infinity of S, the set of all bounded elements in C of S. Okay, so that L infinity of S equal to the set of all F in this space such that F is bounded. Or the set of all F in this space such that there exists an F such that for any X in S, F of X is less than M. This is the definition of bounded function. Now we can use the uniform norm or supremum norm in L infinity of S. By this equality, the norm of F equal to the supremum of all F of S such that S belongs to S. Since F is bounded, this set is bounded subset of real numbers, and so we have the supremum of this set. And this is the unital Banach algebra. It is very, very trivial. So, okay. Thank you very much for your attention. We will continue in the next session, inshallah. Goodbye for now. Goodbye.